Welcome to video lecture B9. This one is on vector space dimension. I'll be your guru, Tom Roby, and here are the outline and objectives. We'll define the dimension of a vector space. It's an intrinsic invariant that captures the notion of its size. And then we'll compute the dimension of several familiar vector spaces. And just to maybe spoil the punchline, the dimension is really just the cardinality of a basis. So it's a very easy thing to define once we've shown some facts about bases. So here's the first lemma that we need. Suppose that V has a basis, B1 through Bn. Then any set in V with more than n vectors has to be linearly dependent, right? The set in V doesn't have to have anything to do with the basis itself a priori. I mean, of course, we can always write everything in terms of the basis, and that's the real point here. So how do you show this? Well, suppose that I've got some set U1 through UP with P bigger than n. And now I'm going to write each of these vectors with respect to the basis. Okay? But each of these vectors with respect to that basis is a vector with n coordinates, right? It's a vector of size n. So, but I've got P of these vectors in R to the n. And we know that if you have P vectors in R to the n, that they have to be linearly dependent, right? Because that's something that we showed long ago. So what that means then is because you can't have more coordinates than you have, you can't have more vectors than you have coordinates, that means that we have some linear dependence relation. So I can just call it, I guess, so we know that C1 times this coordinate vector of U1 with respect to the basis. So remember, that's just, a vertical vector in R to the n plus dot 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 plus CP times UP with respect to that basis equals 0 if they're linearly dependent. Their images in R to the n are linearly dependent. But because this is an isomorphism, this coordinate map is an isomorphism, this just translates back to saying that in the vector space V, that C1U1 plus dot 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 plus CPUP is equal to 0. And so therefore, these vectors are linearly independent in V. Okay? So that means that any set with more than n vectors is linearly dependent. And the other way of saying that is that if you have a set of vectors that's linearly independent, then it has to have no more than n vectors, right? Because if it had more than n vectors, it would be linearly dependent. So if it's linearly independent, then it can have at most n vectors. And so we'll be using that in the upcoming slides. So here's the theorem. Suppose I've got a basis of cardinality n for V. And I claim that every basis of V has the same cardinality. Now, you might think this is kind of obvious, but it isn't something we've proven. So we actually need to show this carefully. Why should it be true that every basis has the same cardinality? Because we can't. We want to define dimension to be this cardinality. And if you could have one basis with 2 elements and one basis with 4 elements, then you wouldn't know what the number had to be. Okay? So here's the outline of the proof. Suppose that I've got another basis C. So C is a basis. I already started off with B being a basis of cardinality n. I haven't said anything about the cardinality of C. But since C, a basis is what? It's a linearly independent spanning set. So because it's linearly independent, it can't have more than n vectors by this lemma. In other words, it can't have more than the number of vectors in the basis B. Okay? But symmetrically, B is also linearly independent. And therefore, it can't have any more, and C is a basis. So B can't have any more vectors in it than C does by the same lemma. Okay? So if I can show that the cardinality, so this number sign just means cardinality. Sometimes people use absolute value signs to mean the cardinality of a set, but I like this notation better. So the number of elements in C is less than or equal to the number of elements in B, but the number of elements in B is less than or equal to the number of elements in C. The only way that can happen is if they have the same number of elements, and that was n just by the hypothesis and the theorem. So this kind of argument where to show two things are equal, you show that, well, inequalities hold both ways is quite common in mathematics. So it's nice to see some of them. Another thing sometimes people do is if you want to show two sets are equal, if you could show that A is a subset of B, and you can show that B is a subset of A, then the only way that can happen is if A equals B. That's not what we're doing here, but it's a similar kind of argument. Okay, so now we can finally make the definition. Usually you make your definitions first and prove your lemmas and theorems afterwards. But here, in order to make the definition, we first need to show this theorem, which basically says that the definition makes sense. So if V is not spanned by any finite set of vectors, then we call V infinite dimensional. What's an example of that? Well, we've seen one already. Basically, infinitely many polynomials. The space, what did I call it? This, which is equal to the span of 1t, t squared, t cubed. But now I keep going, right? When I have p sub d, then I stop at t to the d. But if I don't stop anywhere, then there's no finite list of polynomials that, that spans this vector space of all polynomials. So that would be an example of an infinite dimensional vector space where it's not spanned by any finite set of vectors. But otherwise, it has some finite basis, right? Because if it has a spanning set, then we know that you can always take any spanning set and throw out vectors until you get the linearly independent spanning set, which is a basis. That was the spanning set theorem from before. So either it's not spanned by any finite set of vectors like this, or it has a finite basis B, and we define the dimension of V just to be the size of the basis. Okay? And we'll set the dimension of the zero vector space, which we need to have around, just to be 0. Okay? So if you've got like a one-dimensional, if you've just got a line in R to the 3, then that's a one-dimensional subspace. So it matches with our ordinary ideas around dimension, but it's much more general and very useful. Okay. So let's look at some examples. So what is the dimension of R to the n? No surprise, it's n. Okay? What's the basis? Well, the basis for R to the n is, right, we know what the basis is, so let me just write it down. Script B is just E1, E2, En, right, where these are the columns of the identity matrix if you want to think about them that way. Okay, what's another example? What's the dimension of R m cross n? All the m by n matrices with real entries. Well, you probably remember that this is mn because we have mn basis vectors for it, right? And I wrote them down in the last video lecture for 2 by 3. Right? But the basis vectors are all the things that have a 1 in one coordinate slot and zeros everywhere else. Okay? So that's good. What's another example? The dimension of p sub n, where, so this is, maybe I should have written p sub d, but p sub n, where this is all polynomials of degree less than or equal to n, is, don't be confused by this, n plus 1, right? Because we're really counting from 0 to n, which is like counting from 1 to n plus 1. We're counting t to the 0, t to the 1, dot, 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 t to the n. That's n plus 1 things in a basis. Let me just write down the basis for this one for you. Remind you so that the basis here is going to be 1 t squared, dot, 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 t to the n. And if we were just going from t to the n, that would be n things, so that's n plus 1. OK, next. What's the dimension of the span of these two vectors? Well, take a look at them. I mean, this is going to be the span of any set of vectors is always a vector subspace. This is a subspace of what? R to the 3, right? Because I've got the vectors of length 3. But notice that this vector is just -2 times that vector, right? So that means that this vector, one of these vectors is a scalar multiple of the other. So even though I have two vectors here, a basis for this would just be either one of these vectors. Okay? So the dimension of the span of this is actually equal to 1 rather than 2, because a basis would be of size 1. Just pick one of those vectors. Or some other vector that's any scalar multiple of it, any non-zero scalar multiple of it. All right, how about this one? Well, from this one you see that this is clearly not -2 times this, because it would be that in the first and third coordinates, but it's not in the second coordinate. So therefore, neither one of these is a multiple of the other, and therefore they're linearly independent. These were linearly dependent. These are linearly independent, so this is actually a basis for its span, which means that it's two-dimensional. Okay? And finally, let's take a look at this guy. What's happening here is that if I've got all vectors that look like this, we get these sorts of things when we're solving systems of equations, then let me switch to a more visible color here. Then what does this look like, the dimension of this? Well, a typical vector there is going to look as follows, right? Let's give myself plenty of room. So 2a minus 4c, a plus b minus 2c, and 3b, if I break it out so that it's a times something plus b times something, so what will it be? It'll be a times 2, 1, 0 plus b times, I have b's, I guess I have 0, 1, 3 for the b's, right? Because I have them here and here. And then for the c's, I have them in the first two slots. And I'll have minus 4 and minus 2 and then 0. Okay? So anything that looks like this, where a, b, and c are real numbers, can be broken out into this thing. And so then you say, okay, well, that looks like these three vectors are a basis for that. But if you look more carefully, you'll say, wait a minute. Because notice that this vector, so if I call these vectors v1, v2, v3, notice that v3 equals negative 2 times v1. Right? So that means that these two vectors, I can get anything that I can get as a linear combination of these three vectors, I can get just with the first two or with the last two. I don't need a and c are redundant with each other. So, right, if you wanted to see that quite specifically, you could say, well, this is actually equal to minus 2c times 2, 1, 0. So this whole thing can be written as a minus 2c times 2, 1, 0 plus b times 0, 1, 3. So in other words, I can write anything as a linear combination of these two vectors. These two vectors are linearly independent. So that means that the dimension of this thing, even though I have three parameters, is actually only just going to be, I guess I need to write it, it's actually only going to be 2. Okay. Now this last question is one that's really worth thinking about. What are all the possible subspaces of three-dimensional space? This is the space we live in. It's the one we can visualize. So the first thing you can do is you can just have a point. You can just have the 0 vector sitting in the middle of everything. And that is a perfectly good subspace. So we're going to classify these spaces according to dimension. So what do we get? So we get 0-dimensional. And that's just the 0 vector. So that's all there is. How about 1-dimensional? Well, if I take any non-zero vector and look at the line that spans it going through the origin, that's a 1-dimensional subspace in R3. So this is any line through the vector 0, which is, of course, just 0, 0, 0. So now how about a 2-dimensional one? Well, to get a 2-dimensional one, I need to have two vectors, a basis of two vectors. So that means there are two vectors that are linearly independent, and I look at the span of all those two vectors. And so what I'll end up with for the 2-dimensional case is something that looks like, right, I've got one vector here and one vector here, and those will generate a plane in R3. So that's what 2-dimensional vector spaces look like. And finally, if I have a 3-dimensional subspace of R to the 3, it actually has to be all of R3. So there's no way to have something that's smaller than all of R3 and have it sit in there. Once it's 3-dimensional, it has to be everything. So that's R3. And now, it might be worth, just for the fun of it, to think about what about R4? Well, you still have the same things. You still have a single point, a line through the origin, a 2-dimensional plane, which is, it still looks like a plane even though it's sitting in 4-dimensional space. But then you could also have 3-dimensional subspaces in R to the 4, which are not the whole space. Right? So for example, the simplest one to think about is if I'm in R4, I could look at the set of all vectors of the form 1, 0, 0, 0, or the span of this 0, 1, 0, 0, 0, 0, 1, 0, but I don't include the last one, right? So when I take any linear combination of these vectors, I never get any component in the fourth coordinate. So if I think about it, this as being like x, y, z in time or something, then I'm always at time 0, but I can go anywhere I want in space. Okay, and then, of course, the whole vector space is also always a subset. And that's the only, what's interesting is that you only have one zero-dimensional space, and you only have one subspace of maximal dimension. And then in between, you can have lots of choices. There are lots of different planes that you can draw through the origin in R3 or R4. And there are lots of three-dimensional subspaces of R4 that you can consider, right? I mean, I could throw this vector out, 1, 0, 0, 0, and replace it instead with 0, 0, 0, 1, and I get a completely different three-dimensional subspace of R4, right? One where x coordinate was always fixed, but the y, z, and maybe time coordinate could all vary. So, and let's see, I think that's it for video lecture B9. Thank you for your kind attention.